So let me ask, there was one person who noticed something about the practice quiz. And let's talk about it real quick. I don't know if you noticed anything about the last quiz. There were no questions on the last quiz from section 9.5, the solving trigonometric equations. Geez, I need some more liquid. Mystery liquid. So on this next quiz, what I'm going to do, I'm not going to have any polar graphing questions. Did everybody hear me? So this next quiz is going to go from section 9.5 up to 10.3. So it's going to have trig equation solving, and then it's going to have law sines, law cosines, and then it's going to have the basics of polar points, converting between polar and rectangular and vice versa. But there won't be any graphing polar equations. Okay, maybe. You guys okay out there? Is that good? Do you hate that? Do you want me to include 10.4 on there also?
No,
Give me a thumbs up if you like not having 10.4 on the next quiz. Oh, this is where you, oh man, let's see. I better get more than half of you. Oh shit, man. This is where those people that log in and walk away, you're screwing everybody over. Oh, here we go. Look at that. I got a few I can see, and I got a few in the chat. Okay, that works. That works for me. Okay, thank you. So it's just a few people that aren't here or abstaining. You can abstain from the vote. That's your right. Okay. I'll just assume you're abstaining and not sleeping on the sofa. Okay. Anything else from homework stuff, or you guys saw that the practice quiz is up there? I'm going to unlock the solution video soon. Okay. And the quiz, of course, is on Thursday. Okay. If there's no questions, we're just going to jump right back in to where we left off. We're going to do some more polar equation graphing. Should be exciting. And the very first thing we're going to talk about, actually, let me see if I can do this. Let's see how lazy I can be. I could be very lazy. Do I want to do this? Maybe. I don't know. I kind of like this. All right, here we go. Let's see. Oh, shit. This isn't going to work as easy. Damn. All right. Let me see. I'm going to have to do this anyway later when I do the polar graphs. All right, here we go. Yes. All right, I'm going to have to turn my Death Star off. All right. I'm sorry. Let me see. Let me turn my Death Star. No, it's not the Death Star. It's the Cloud City. All right. I forgot. All right, hold on. Pop. And then I can just do this. Wee-haw. Most intriguing. Let's see. TV work. Go away. All right. All right. Sweet. So if you weren't here yesterday, all right, this is weird. Can you just rotate? Okay. We did this yesterday, right? We did this. Oh, shit. Hold on. It's a little fuzzy. Let me help it out a little bit. Bam. Okay. Right. Does that look familiar to the people that were here? We did some of that. We did some of this. Right. We started graphing a basic graph. We graphed. We talked about conversions, and we talked about, ooh, that's a neat graph there. Okay. All right. Now, so what we're going to get into, let me see. I just need some blank paper. Okay. And I need a pen. There you are. Let's see if I can orient myself. Where we're going to get into is symmetry. Oh, this is going to be weird. All right. This is interesting. I like this. So somebody remind me, what do you know about any kind of symmetry that we've talked about? Anybody know anything about any kind of symmetry?
Odd and even symmetry.
Odd and even symmetry, kick ass. So let's review a little bit, because there are going to be some similarities between rectangular symmetries and polar symmetries. So a little recall. What was even? Somebody else tell me what was even symmetry. What's kind of like a picture that represents even symmetry? I like it. Awesome. Looks like you're about to do a magic trick. What?
Cosine.
Oh, okay. Yes. Cosine now will work. But something even more basic than that would be like a parabola, but that captures the idea that it's symmetric with respect to the y-axis, correct? All right. Is that close enough for you guys? Can you see that? I guess it's all right. What about odd symmetry? Somebody else?
Sine.
Sine. I like it. So sine is like this. Does anybody know officially what that is? So this is symmetry with respect to the y-axis. What is the symmetry with respect to for odd? Anybody remember? It was a very strange thing. The symmetry with respect to, I like it. Looks like, oh man, Jeff, all right, I'm gonna make a dad joke. It looked like Charles was just dabbing. So I'm sorry I made that joke. But I understand what you're saying. It's symmetry through that point. It's symmetry through the origin. So this point, if there's a point mirror there, then it would also show up on the other side. Neato. So how much do I want to say about this real quick? If I have an axis, now stay with me. This is really cool. I just want to get into this a little bit, because is anybody still freaked out about what the shit symmetry through a point really is? Anybody freaked out about that? Or are you guys all just cool with it? You're like, doesn't this make sense? This is a freaking mirror. That makes sense, right? What the hell would a point mirror be? Nobody's worried about that? You're all like, I accept it. Why not?
I mean, I kind of relate it to in artwork. It's like distance. So like everything lines up on the horizon.
Yes, artists use
Through a
very
point.
similar tactics like this. I like it for doing the horizon. What is it? The vanishing point and all that kind of business.
Exactly.
But here's the way I think about it. Every point on this y-axis, a point on either, this would go through and be there. So it's like this is an infinite number of points that this is symmetric with respect to. And this one, this is the only point. So every point has to go through it. Every point here has to go through it. It doesn't have, here I am motioning to you and you can't see me. It doesn't have the whole line to work with. Okay. All right. I'm going to stop talking about that. Okay. So let's come to polar symmetry. All right. We already saw. All right. So remember, where's the one I just did? Well, shit. It's on the, I think it's over here. Is there another side of this paper? Yes. We did this picture, which is r equals 5 cosine theta. What kind of symmetry? This is a new kind of symmetry that we didn't officially have before, but what is this symmetric with respect to? Is it symmetric with respect to the y-axis or the theta equals pi over 2 axis?
No.
No. What axis is it symmetric with respect to?
X.
X-axis, which
R.
interesting. Now that gets really neat, the idea of an R-axis, because the R-axis is wrapped around. That's not exactly right, but that's a whole other thing, dude. But let's not go there. So I like that. I obviously cannot call this the x-axis. That would make no sense because I don't have any freaking x's in my polar coordinates, correct? So another way the reference is the theta equals 0 degree line. That's kind of boring. We actually call this the polar axis, which is much more interesting. It either sounds like a sequel to the Polar Express, or it sounds like, I don't know, some dumb ship name from Star Wars. What do you think? The polar axis. It did the thing in 14 parsecs. It's not a measure. All right, sorry. I'm sorry. So we call this the x-axis in the xy plane is called the polar axis in polar coordinates in the r theta plane. Everybody with me? So this thing, obviously has that symmetry. So what is that? How can I tell? So this point is symmetric to that point. I mean, it's got a mirror image here, correct? All right. And can you tell, for example, so how do I test that in general? Let me think, how do I say this? For some given angle, the negative angle gives me the same output. Would you guys agree with that? For any angle, the negative angle gives me the same output, correct? I like it. And sure enough, so let's see, let's make this official. So symmetry with respect to the polar axis, which is theta equals 0 degrees, which is related to the x-axis. All right, now stay with me, sorry. This is sort of a brand new symmetry that wasn't part of either of these, was it? Neither of these is an x-axis symmetry. Why didn't we have x-axis symmetry before? Because we were dealing with functions. Could a function have x-axis symmetry? Is this a function? Is this a function?
No.
Hell no, right? But now that our axis, now that our radius axis is now curved, I'm allowed to have that kind of symmetry. It's allowed to curve on itself because that's what the coordinates system does. It curves back on itself inherently. All right. I don't know if you guys are still with me or not. But the test for this is if I replace r theta with r negative theta. And that's basically what I just said, right? If I put the negative angle in, I should get the same output for r. That would mean it has polar axis symmetry. So let's try it. Or to be honest, there's another or with, this gets a little bit freaky, but some of you guys might realize this is a sort of an identity. If you replace r theta with, what was it? Negative r pi minus theta. All right, so watch this. This is kind of cool. So if we take this equation, r equals 5 cosine theta. Now let's replace r theta with r negative theta. Who remembers what r cosine, what's cosine and negative theta? What's cosine of negative theta?
Cosine theta.
Yeah, because it's got even symmetry. So this will be r equals 5 cosine theta. Do I end up with the same thing? Yes, check. All right. I can tell by some of you guys' reaction. This is kind of boring. That's not bad. This being boring is not bad. Let's try this. Let's replace r and theta. Let's replace it with negative r and pi minus theta. All right, this is going to get interesting. Maybe. Stay with me now. You don't even need 5-hour energy. You just need an hour and a half energy if you can only afford that much. Now, does somebody remember what this is? Cosine of pi minus theta. Or can you think, so for a given angle, theta, what happens? Where's pi minus theta? If that's theta, where is pi minus theta? Where's pi? Where's pi?
Quadrant 2.
Not really, because it's this axis, right?
Yeah, actually. Yeah.
Okay. So where's pi minus theta? I'm sorry. So maybe you're answering that question. Where's pi minus theta? Here. Isn't this going to be the reference angle? Now think about it. What's true about cosine of this angle versus cosine of this angle? How do they relate? What's cosine back here? How is it different from cosine over here? Come on, guys. Cosine back here. Is it going to be positive or negative?
Negative.
Negative, because it likes x. And what's cosine over here? It's positive. So what do you get when you do cosine of pi minus theta? You get negative cosine theta. So negative r, so the negatives cancel. Do I end up with the same equation? Yes, I do. Check. So I got polar axis symmetry, which also is x-axis symmetry. Cool. Aw, little person. All right. She heard polar. She thought it was polar express. I'm sorry. Second kind of symmetry. So let's go back to the one we should expect. There should be symmetry with respect to the y-axis. What do you guys think we're going to call the y-axis here? We're going to do it the boring. We're going to choose the boring way. Remember, I called this the theta equals 0, and we have a cool name for it. So what's the y-axis? I already put the answer down. That's funny. Right? The y-axis is theta equals pi over 2. Isn't that if I graph theta equals pi over 2, it would be all of these points. That's where theta equals pi over 2. Okay, so that's the y-axis. So how would you have symmetry with respect to theta equal pi over 2, which is related to the y-axis? It doesn't have a cool name. I'm sorry. We can call it the perpendicular polar axis. Perpendicular? No, all right. So what would this take? Let's see. So something like if I did r equals 5 sine theta, it would look roughly like this. Just go with me, right? So this is definitely symmetric with respect to the theta equals pi over 2 line. Everybody with me? So how do you think that would translate? This gets a little bit weird. Let me see if you guys, all right, I don't know if you guys can come up with, it's not as easy as the other one in a sense. Think about this. If I do theta and I go out 4, I still want to go out 4 here, correct? But all right, let me just give it to you. So this is the point 4 pi over 3. If it has symmetry with respect to what we call the y-axis, theta equals pi over 2, then I can go to negative pi over 3 and go back 4. Doesn't that work? So if I go to negative pi over 3, so I make the theta negative, and I make the r also negative. So if I replace in the equation r theta with negative r negative theta, and it comes back to what it was, it's got symmetry with respect to theta equal pi over 2. Oh my God, I'm boring myself. I'm sorry, but this is still, we got to get through this. Stay with me. So coming back to here, if we do an example, oh, sorry, let me write down. If we replace r theta, Jeff, with negative r negative theta, and it's the same, then it's got theta equal pi over 2 symmetry. So let's try it out. So example, r equals 5 sine theta. So if I replace it, the r with negative r and the theta with negative theta. What is sine of negative theta?
Negative sign.
I like it. And of course, then the two negatives cancel. So do I end up with the same thing? Check. So we knew this thing had freaking this symmetry. So of course it better, pass the check. We already knew it had that symmetry. Okay. I like it. By the way, all this is in the book, and they got it in one of those little nifty boxes. So if you don't want to write all these notes down, you can just go in the book and you can find it. All right, let me see. How much room will I give them myself? Do I want to go another sheet of paper? Maybe. No, it's going to be semi-quick. What was odd symmetry? Odd symmetry with respect to the origin, right? So there is one like that. There's with respect to the origin. And the nice thing is we do give the origin a nifty name. We just call it the pole. Call it the pole. I like it. Sort of like flat earthers who believe the North Pole's in the middle. Do you guys know? Do I have any flat earthers here tonight?
Totally.
If so, you're in the right place. You're going to college. That's good. Maybe you'll join the rest of the world. If you didn't know there are flat earthers that still exist out there, there are so many. They scare me. All right. Anyway, I'm gonna stop joking them. I'm sorry. So with respect to the pole, which is really another name for the origin, right? When we have polar coordinates, we got to call it the pole just to make it all nifty. To have this, you have to, if you replace r theta with, you might expect this, negative r theta. So if I replace r theta with negative r theta, isn't that just make sense? That has symmetry through the, you can see it, symmetry through the pole, bam, symmetry through the center, correct? Well, let's see. What's a good example of this? I didn't think of an example ahead of time. I mean, it's kind of dumb. One of the easiest ones is r equals 5. What is that the equation for? What would that look like if I graphed it? R equals 5. No? Yeah, okay, it would look like a circle, right? Circle of radius 5. If I replace r with negative r, do I get the same thing? Of course I do. We talked about that yesterday. I still get the same thing. R is negative just means go back and then get them all. Instead of going forward and get them all, I still get the same circle. That's a really pathetic example, but oh well. So you are able to test an equation for symmetry, and what that will do for you is it will decrease the amount of the table you got to do, the r theta table. All right, so let's do this. Let's try a funkier equation and let's see what happens. This is gonna be exciting for me because I didn't do this ahead of time. So let's see what happens. Oh shit. Let's do this. If I were you, I would be most curious about the graph of things when I put a number inside, something like, let's do 4 sine of 2 theta. You guys with me? I want to see what that does. What effect will that have on the graph? Now, first off, let's test that for symmetry. Right? Do I have any? All right, guys, stay with me. Stay with me. I don't know. Is this format where I'm writing on paper? Is it making it worse? Is it making it more boring? Or am I just boring and there's nothing you can do about it? I understand.
It actually helps me a little bit.
Oh, good.
It helps me follow along a little bit easier.
It's helping me stay a little more clean with what I'm doing. Plus, I've got this right here, you know, that I need anyway. Anyway, all right, Jeff, what are you doing, buddy? I got no blank paper to save my freaking life. Here we go. I can save my life. Okay. Let's test this sucker out for symmetries. All right. So I don't know how good of a notes you just took, but how do I test this for symmetry with respect to theta equal pi over 2? Let's start with that. Does anyone have that written down in your notes? What do I replace r theta with?
Negative r, negative theta.
I like it. Negative r, negative theta. Go ahead and try. So take the equation, replace r with negative r, replace theta with negative theta.
Yes.
Yeah, because what's sine of negative angle? What sine of negative angle? Yeah, the negative comes out. So the negatives would cancel. So I do end up with the same equation. Is that cool? You guys with me? All right, we should be able to expect that. A lot of sine related things are going to be symmetric. And why does that make sense? Because I didn't teach you SOHCAHTOA shit. I taught you sine likes y. So look at this shit. Sine likes y, a lot of sine stuff with respect to the y-axis, right? Theta equals pi over 2. All right. Sorry. Those of you who love SOHCAHTOA, use it. I don't give a shit, whatever. Just understand the other way because that's going to be much more useful. All right. What about with respect to, let's see, what do I want to do next? The polar axis. Polar axis, which to remind you guys is theta equals 0, which also is the x-axis. So what do you guys have written in your notes? I want to replace our theta with what? This is where you have an option.
R minus theta.
Theta, yeah. Now it is possible for something to have all of the symmetries. Right, so don't stop when you find one symmetry. It doesn't mean they're done because it could have multiple symmetries. But I mean, this one should kind of tell you it's not going to work, right? Because of what we just found earlier. So this would be r equals -4 sine 2 theta. Do you get the same thing? No. Now remember, you could also replace it with -r pi minus theta. Right? Sometimes that might come out different, but not here. And I think the only one we left out so far is respect to the pole. Oops, shit, I better write somewhere you can see what I'm writing. With respect to the origin, 0, 0. And of course, that's where I replace r theta with -r theta. And we already know that's not going to work, right? Yeah. So if you're not sure how you could possibly have all three symmetries, remember I can have stuff squared, correct? Squaring stuff will make this happen. Yeah. So this doesn't have anything squared, so it's pretty much dead from the beginning. R equals -4 sine 2 theta, which is not. So no. So I only have basically y-axis symmetry, which I'm just going to write here because we're more used to the y-axis, but just remember that's not the right way to reference it. It's theta equals pi over 2. All right. So what that means is if I plot what's happening here, I can just mirror image that shit over here. Do you guys understand? That's beautiful. It's beautiful. All right, so let's do a few things. Let's see. Am I going to have enough room? Maybe, if I can do this right. I might have to do over here. Okay. So obviously, we'll plug a 0 in. And what do I get when I plug a 0 in?
1 or 4.
What? What's sine of 0?
0.
Oh.
I like it. Now watch this. I'm going to put pi over 12 in. Because I'm crazy. Because then what do you get when you plug a pi over 12 in?
2.
Let's go step by step. So pi over 12 times 2 is pi over 6. The sine of pi over 6, it was 0. It's growing a little bit. Now it's a half. So a half of 4 is 2. Okay. All right. I like it. Hey, Mikey. All right. And then pi over 6. When I plug it in, it's becoming pi over 3. Sine of pi over 3 is rad 3 over 2 times 4 is 2 rad 3. which is roughly 3.5. I don't know. Somebody help me out. Are you guys cool with what just happened? Pi over 6 times 2 is pi over 3. Sine of pi over 3 is rad 3 over 2 times 4 is 2 rad 3.
3.46. So yeah.
Sweet. Look at me doing shit right. 3.5. I like it. And then if I'm plugging in pi over 4, twice pi over 4 is pi over 2. Sine of pi over 2 is? Sine of pi over 2 is? Sine of pi over 2 is?
1.
1.
1 times 4 is 4. Okay. So you can see it, sine is doing what it's supposed to. It's kind of slowly building up to its maximum. How do I know this is the maximum? Because this function is maximal when its input, when it's inside, is pi over 2. And that's what we just got. We just got a pi over 2 on the inside. Okay, all right, I love it. For some reason, I feel like I'm being extra boring today, but stay with me. Okay. Let's plot what we have so far. I love it when we get to point 0, 0, because it's kind of like, have you ever seen, they used to have billboards that would tell you how, if the wind was, so like 7 from the northeast, it would say 7 miles an hour from the northeast. So I always loved it when it was 0 miles per hour from the west. I'm like, excuse me? What? If it was moving, it'd be coming from the west. Anyway, so 0, 0, it's kind of weird. It's like you're not, where are you facing? It doesn't matter, but you're facing 0 and you don't go anywhere. There's 0, 0. Pi over 12 goes to 2. So we'll just use the natural scale here, right? When meaning 1, 2. Is that right? Yeah, pi over 12. Jeff, you can't look at the screen. You get all freaked out. Pi over 6 goes to 3.5. So 1, 2, 3.5. Pi over 4 goes to 4. So 1, 2, 3. Pi over 4, Jeff. 1, 2, 3, 4. This is looking interesting. Sort of. Now watch this. The more you understand trig functions, the quicker this is going to be. Didn't we just hit the maximum? Doesn't sine build up to its maximum, and then what's it do? Does the same values back down to 0, correct? Do you guys understand what I'm saying? So I know it's going to go like this. I know it's going to just, so I know, all right, let me see if you guys are with me. I'm going to make some predictions. I'm going to predict that here, it's going to be here. I'm going to predict that here, it's going to be here. And then here, it's going to be back to 0. Because that's what sine does. Sine builds, and then it decays.
Is it symmetry on pi over 4?
What do you mean? Oh, no. You don't say it's symmetric unless the entire graph is symmetric. And I mean, now listen. I feel weird that I can't look at you. You can't look at me, but for example, would you say, I want to make a broader point. Would you say that this graph has no symmetry at all?
Yeah.
Oh, come on. Isn't it symmetric with respect to that line?
Yeah.
Is that an officially recognized symmetry?
Yes.
No. Is it odd? No. Is it even? No. So it doesn't have a generally accepted symmetry, but it does have its own symmetry, correct? This is a line of symmetry. That's what it's called. So I need you to understand, this is just a definition thing, okay?
So you say it's not offshore?
Say again.
Did you say it's not offshore?
Not official. It's not one of the main types of symmetry that a graph can have, but that doesn't mean that it doesn't have some kind of symmetry.
How about what is an offshore symmetry line?
Oh, well, that's the ones we identified, even, odd for x, y. And then there's respect to the polar axis, respect to theta equals pi over 2, respect to the pole for polar coordinates. But you just identified a localized symmetry for this graph, correct? There's no way necessarily And there's no reason necessarily to test that in general. Does that make sense?
It looks
Okay.
like your point for pi over 3 is just a little bit off.
Uh-oh, shit. Yeah, I agree with you. Why did I do that? And I'm doing it in pen too. Yeah, it should be halfway here, right? Let me do this. Get out of there. All right. Dadgummit. See, kids, this is why you should do everything in pencil. Why am I doing this in pen? So it actually shows up for you. Okay. Now, what do you think is going to happen back here on this side? What did we go into this knowing? Didn't we test something going into this?
It's symmetrical over or across pi over 2.
Yes. So I know there's going to be another one of these here, right? All right, now let's keep going because look, now watch. I want you to realize something. If you go ahead and connect these, all right, Jeff, go to the right one. There you go. Austin helped you. Where does it look like it's headed now? Do you see? Where does it look like it's headed now? Isn't it headed down here? Does that make sense? It's going around. Isn't it look like it's headed down here? Just kind of naturally, no?
Yeah, it kind of looks like that.
All right, let's see if it does. Let's see if Jeff is full of shit. All right. So, and by the way, I don't know if I need to do this, but just to make sure you guys believe me, if I put pi over 3 in, what sine of 2 pi over 3? You can do it. What sine of 2 pi over 3? It's the same as sine of pi over 3, right? That's the reference angle, correct? And what's the sine of pi over 3? It's closer to the y-axis. Hello? Hello?
It's 1/2.
No,
Oh, sorry.
closer to y, so it's bigger. It's rad 3
Yeah,
over,
it's the rad 3 over 2.
and rad 3 over 2 times 4, we did earlier, is 3.5. So it is going through all those same values. It built up, and now it's going back down. Okay, really, if the less you understand that, the more complete your table should be. That's okay. You might have to plot some more points. That's fine. But the more you understand, this is my favorite saying, the more you understand, the less you should have to do. Right? The less you understand, the more you got to show yourself, the more you got to do. All right. So let's pick up right here. So this is pi over 2 is the last thing we put in kind of unofficially here. We just kind of, so let's put in the next thing. Let's go, well, should we do 7? Yeah, why not? Let's put 7 pi over 12 in. Okay, so this becomes 4 times sine of 7 pi over 6. I want you guys to realize, some of you guys are going to really hate this. Anybody who hasn't actually memorized this shit, or some of you guys are going to be cool with this because you're just going to plug this shit in the calculator from the beginning. I understand. But you know Jeff is going to have something on the final where you're not allowed to use a calculator. So you should know this shit. Okay. So sine of 7 pi over 6, that's related to pi over 6. 7 pi over 6 is in which quadrant?
The third.
Yeah, so sine is going to be
Negative.
negative. It's close to the x-axis, so sine is going to be small. So it's going to be 1/2. Negative 1/2 times 4 is going to be negative 2. So can somebody tell me what their prediction is for the next thing? See, we're at negative 2. What's your prediction for the next thing?
Negative 3.5.
Yes, I'll bet you anything is going to be negative 3.5. Let's find out. 4 times sine of 4 pi over 3. Is that cool? Because if I put a 2 pi over 3 over here, it's times 2 is 4 pi over 3. Oh, I can feel some of you guys out there like, oh my God, this shit. Help me. Okay. But remember, you should try to do this in your head somewhat, you should try to, and then you can just plug in the calculator, right? But sine of 4 pi over 3 is negative rad 3 over 2 times 4 is negative 3.5 again. Do you guys understand? So I'm not going to do any more because I already know the next thing is going to be -4. And what am I going to get? Now watch. Let's see. Oh, this is going to be neat. So how do I plot this point? I face, and by the way, just to make sure I'm not screwing you guys over, can somebody tell me officially what point this represents, this work? What point does that represent? It's all janky. All right. Help me, help me.
-2, 7 pi over 12.
Thank God. All right, right? R theta is the official order.
Over 12.
Over 12, thank you. What am I doing? All right, R theta is the official way to write polar coordinates. I'm really hoping that me doing this doesn't screw that up, because you don't want to turn this around and the teacher's like, who did you have last semester? I had Waller. He sucks. All right. I just personally like inputs and outputs, and theta is most often seen as an input here, right? Okay, okay. All right, so don't let me screw you up. So let's try to plot this. How do I plot this point? I'm going to face 7 pi over 12, but I'm going to go where?
Back 2.
Back 2. So again, there's that stupid optical illusion, like which of these spaghetti things is the free? So you just go to the one that's over 12 on the side, right? So I'm going to go back to 1, 2. There's the point. And this is kind of neat. Now, I'm going to point out something about symmetry here in a minute, because it looks like this is going to have symmetry with respect to the x-axis kind of thing, right? All right, let's keep going. Oh, so we already know what's going to happen, right? The next thing is going to be -3.5. So I face 2 pi over 3. So I'm going to go back 1, 2, 3.5. Then I'm going to go back 1, 2, 3, 4. Is everybody cool with that? I'm kind of cutting some corners, but I mean, I know it's going to go 2, -2, -3.5, -4, and then it's going to build back. So now it's going to get, now I've reached this minimum point. So now I'm going to start going and go back. I'm going to go back. Jeff, you can do it. There you go. Look at you doing it. And then I'm going to go back there. So now it's going to go like this. So look, I really want this. Do you see how I'm going around? And then I just kind of naturally keep going. Jeff, dadgummit, you crazy person. Another reason why pencil is good. Do you guys understand what so I go back, and it's just natural. It would be really unnatural for it to suddenly go over there or something, or to definitely go over there would be unnatural. Around and then around. And then why am I basically done? Because we already established the symmetry it definitely officially has. So it's going to basically do the same thing. So I can it's going to have this symmetry. This is going to be symmetric here. You could do it, Jeff, can you? There you go, buddy. Then it's going to have the pi over 4 is going to go out to 4. Is everybody with me? We already know it's got this symmetry, so I got a lot less work to do. And you can even just sort of stop plotting points and just sort of drawing. I don't know. I like the points. Points are good. Did I do that right? No, you did the same thing.
It's 3.5.
Rawr! Well, this is fine. I'm showing you that no matter how much you know, you can still make mistakes. And then it basically goes here. Oh, Jeff, come on, you're better than that. And then, so it goes around, wait, it goes around. Oh, it actually is it would do this one next. Do you see that? And then it would do this one last. And then it would just retrace this forever if I kept going with my theta. Gosh darn it. So now down here, it's going to be symmetric here. You can do it, Jeff. You can do it. You can do it. Look at that. You deserve a cookie. All right. And then here, and then there, and then there. So there's my last little leaf.
Like doing laps on a freeway clover.
Exactly. If you've ever been out to Dallas or somewhere, Dallas is especially in my head. All right, mine is a little bit wonky. It looks like a butterfly somebody sat on, but oh well, poor little thing. Poor little thing. And here, as long as I got this all set up, if I do this, go to polar, you can do it, Jeff, and put in here, go away. What was it? 4 sine 2 theta. Now watch this. If I go to my window, no. If I go to my what do I want to go to? I don't know, Jeff. Why do I forget? Oh yeah, window. I think I showed you this before. I don't know why. Now stay with me, stay with me. I don't know why it chooses such a large step size, because what angle am I going up to, by the way? What angle is this? Theta min is 0, theta max is
2 pi.
2 pi. I like it, right? That's twice 3.1415, blah, 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 blah. If I graph it right now, it's gonna look, it should look a little bit too linear. Also, let me do zoom 6 just to give it a standard window. No, that's not too bad. Let me zoom in. Let me see if it zooms in too much. Yeah, it did. You stupid thing. Zoom 6. All right. Anyway, so that pretty much establishes we got the right answer. Let me see if it gets any. Oh, that's different. What happened? When did I do that? Was I in degrees? What the shit? All right, that definitely goes freaky. All right, that's better. Sorry, guys. All right, let me go back to this. If I make this a little bit like 0.05, it should get a better. See, it wasn't that bad, to be honest. If you notice your graph, if you're trying to graph something on the calculator and you notice it's getting a little bit like linear, then you want to change your step size. The step size is basically how far does it calculate the next point? How far does it calculate the next point? And of course, it's like a resolution, right? It's a resolution issue. You guys okay out there? Are you guys okay? Yeah.
It makes sense, yeah.
Okay. So again, here, let's do this. All right. Let's take a break from this stuff here. Let's do something on Desmos. Oh, where are you? Let's see. I have something set up here. Where do I want to put it? Here, I guess. Where'd you guys go?
I thought that we found out that it wasn't symmetrical.
Oh, yeah. Okay. All right. So there is an interesting thing because of the 2 theta. If I do this, you can't see my freaking mouse, can you? Because of the 2 theta, something interesting happens. I get a symmetry that's not a recognized symmetry. What do I mean by that? What is, all right, stay with me. This is really a little technical, but I did say I would talk about this a little bit. What is symmetry with respect to the polar axis, right? Who still has their notes right there? How do you figure out symmetry with respect to the x-axis?
Change R minus theta.
Well, change r theta, yeah, to either r negative theta or negative r pi minus theta. Okay. Right? That was how to check it. Did we check this one?
No, I don't think so.
Let's see. Let's check. No, I'm trying to remember myself. Well, let's see if this works. There's one of 2 situations for this graph. Let's see if this is the situation it's in. So if I take r equals 4 sine 2 theta, and I'll replace it with negative r, and I'll replace theta with pi minus theta. Shoop. Now, how are we gonna evaluate that?
It's minus sine theta.
Yeah. So this becomes negative r equals 4. Because it doesn't matter the 2's here. What matters is what happened here. This is going to be negative sine of 2 theta. And the negatives cancel, so I do get back to the original. So this is why this test, there is another situation that doesn't quite follow either one of these, and I couldn't remember which one this was. But that's why if this one doesn't work, you have to try to check this one also. Okay. And that would have cut down our time a lot more. I don't know why I didn't do this one earlier. So I made this longer than it had to be, but well, maybe that's why I did it. Now it's coming back to me. I wanted to do more with the tables. Okay, anyway. Is that better? That's why there's like two options here, because if one doesn't work, the other one might. All right, now what was it I wanted to do next? Oh yeah, Desmos. Any other questions on this problem before we continue? And by the way, let me show you this too. Yeah. All right. Well, okay, no. I'm not going to do it on there. Let's do this. Just go to Desmos, Jeff. All right. No, don't show them your taxes. I was doing my taxes earlier, finally. All right, here we go. Where'd you guys go? Oh, I love all of this. All right, nothing's easy anymore. Here's Desmos. Okay. All right. So what I've built in here is kind of a little more complicated equation, right? So let me see. If I put in here R equals 2 plus 3 sine theta, you get this. Maybe. So a more interesting way, the beautiful thing, let me kind of do this over again. Let me show you how easy this is to do in Desmos. So I'm going to type in here R equals A plus B sine theta. And then look what it asks me. Add a slider for all. And now I can do this shit. Right? Isn't that cool? Let me change. Well, let's see. That's fine, Jeff. All right. So now I can investigate what happens when I make A bigger. Well, when I make A bigger, how would you guys characterize? I mean, there's an obvious thing. If I make A bigger, the whole thing gets bigger. But can somebody be a little more specific about what happens when A gets bigger?
The shapes get changed.
Shape changes, becoming more what?
Circular.
Circular. I like it. I feel stupid that I don't remember how to change the color of this. But oh well, too bad. I want it to be blue or something more to stand out. I forgot how to do it. Braille mode. No, thank you. Oh well, I forgot. Too bad for everybody. Now let's take this back. What happens when I increase B? Anybody?
2 circles.
Yeah, both circles, the inner one and the outer one, get bigger, correct? Now watch, if I put B at 2 and I put A at 2, now watch. A is not 2 yet, correct? So let's see, what happens, I approach 2. Can somebody tell me what happens there? I'm at 2, what happens? What's special about when these are the same?
They kind of like equalize, right?
Yeah, and is there an inner circle anymore?
No.
Sorry, a little dirty into the butt graph here. Sorry. All right. Now, so the cool thing I want you guys to realize, I mean, I love graphing calculators. They're awesome. They're fun to play with. But this is more powerful because it's much easier to change. What can somebody please guess for me? What's going to happen if I put a cosine here instead?
It's sideways.
Yeah, right now it's opening around the y-axis. Can you see what I mean by that? So of course, if I put a cosine there, it should open around the x-axis because cosine likes x, of course. And if I go negative, look at what happens if I go negative. It just is the same stuff, right? For the A, let's see what happens with the B. Ah, that's more interesting. Now it switches sides when I make the B negative. All right, sorry, you guys are bored again. I'm sorry. I was trying to see if a change in multimedia presentation would make it less boring. All right. But this, I mean, I want you guys to realize you have Desmos in Canvas. So let me see, what's another good one? I can even do r squared equals a cosine b theta, right? Just throw something in there and make a slider. Oh, why aren't you like, oh, I see, because I should make this squared also. Let's see if it likes that better. Or is it, let me think, what am I doing wrong? I'm doing something very wrong. What does it not like? Oh, it doesn't like something. Oh, it doesn't like the r squared? Oh, that's too bad. So you can't do that. Okay. That's too bad for everybody. Let's see, does it like that better? Still doesn't like that. All right. There. Okay. Ooh, I'm sorry. I am very sorry. I'm so sorry. But look at this shit. Now watch what happens when I hit it. See, look, I'm on an integer, correct? The minute I'm on a decimal, it's kind of like, I really want this to kind of make sense. What am I controlling with B? Let's go back a few chapters. What am I controlling with B? What does that change?
Isn't it like the amplitude sort of?
No, that's A.
Oh, okay.
What does B do?
Change the angle.
No, come on. What's the official name for what B does? Let me call it K instead. Is that better? No. It changes the period. It changed. I really want this to make all the sense.
Oh, okay.
If I have a decimal period, it's offset. It's not going to kind of, I really want you guys to understand, it's not going to kind of draw over itself. But the minute I hit a whole number, it's going to draw over itself. It's not offset. But if I change the period to be something weird like a decimal, now it's offset. But when I hit an integer, you guys with me out there? Sort of, a little bit.
Does that mean like on the decimal ones, it has to go several times around to get back to itself before it starts tracing itself?
Yeah,
over
yeah.
again?
The worst. So let me see. How do I change? Okay. Let's see if this works. No, I forgot. Somehow I can change. Anyway, I should be able to change how much this steps by. Maybe if I put this in here, sorry. So yeah, if I make it a decimal that goes out more places, then it's gonna have, come on, you can do it. Why won't you step like this? Do it. You won't. Well, screw you. All right. So Desmos does not have as much power as I thought. All right, that's fine. But yeah, one decimal place off. I like what you're saying. It would eventually catch up back with itself. Let's do this. Let's
It
increase.
just takes some more rotations around pi or 2 pi to get back to itself than normal.
Oops, shit, didn't mean to do that. You got it. Exactly. That's exactly right. So if this was worse, this decimal was worse, then that offset would be worse. And there's even a possibility that it never, especially if you put like an irrational number here, it would never come back on itself. Yeah. Anyway, I don't know if I went too far for you guys. Look at the inside. Look at this. Isn't that neat? Anyway, sorry. Anyway, so I mean, you can just type all kinds of weird shit here. You got to be a little careful, I guess, because Desmos does get a little bit antsy about things. So what about a sine b theta plus c cosine d theta? Look at all. Now I got all kinds of shit. Oh, dude. Oh, dude, I could play so much. Look at that. It's kind of like offset. Oh, look at that. I mean, all right, I'm sorry. I'm just playing around now. I know. Look at this shit. Would you look at this shit?
What would something like exponential look like?
How do you mean?
Well, that's what I'm kind of asking.
Oh, how would you capture?
Yeah.
It's interesting that you bring up exponentials because they get really nifty how they interact. But you could, I mean, so there's something like you could do r equals, I mean, this is dumb. A theta just makes a spiral. But if you do something like, let me see, how do I say this? A to the sine theta. Let's see if it can handle this. Yeah. Is that sort of like what you're talking about? I got too many see, I could put it.
Well, yeah, sort of. Yeah.
All right, let's see. There you go. See B again, so I put B in there, so that's the period thing. So it's all about if it's going to be able to redraw over itself, right? A is interesting in this case. A is something we're not used to. And again, guys, I'm just playing around here. Are you guys with me? You're not going to suddenly have to know all of the ins and outs of this. Are you with me? Austin just said exponential, and I thought, yeah, let's put it in there.
Yeah. All right.
And I remember playing around with these a while back where you get this neat little inner starfish thing. Right? And then when you go negative, now, why do you think it's going to have a problem? Look, it has a problem back here. Because you can't have a negative base, because if the power is like a square root or something, it goes imaginary. So it just kind of doesn't even try if it's the negative base. Okay. I like it, but B can be negative, of course. Anyway, I'm sorry. That's enough. I'm just playing around now. I could sit there and play with that. Oh my God, for freaking ever. I don't know if anybody else feels anything at all the same way. All right. Holy shit. I look like somebody's drunk. All right. There.
And one of my favorite things my mom got me when I was very little for art was like, it's like a little gear that fits into a thing. And stick a pencil in it, and it spirals.
Spirograph.
Yeah.
Yes, I had one of those when I was a little kid. They had all different sizes of gears.
Yeah, and even weirdly shaped ones, like one looked like a T with teeth on the ends.
There you go. So we are learning the equations behind what the thing did. Now, if we went further with polar, and of course, polar coordinates are just a small part of this course, right? This crazy ass course where we pack so much into it. And you guys are all like, yes, this is so true, Jeff. We put a lot of shit in here. I know we do. But it's just supposed to be introductory for all these different things. You go further in math, you can actually get to the point where you understand what the gears do to the equations. This gear would change this variable, and this gear would change this variable. And if you put this gear inside of this gear, you kind of follow what I'm saying? So it connects the gears with the parameters of the equations. So you can actually get the equation for what a thing would look like before you do anything with your pencil and the gears. Yeah. Anyway, whew, I'm tired. All right, hopefully somebody was still with us here. That's enough for tonight, I think. So quiz is still Thursday. I'm gonna put I'll go ahead and unlock the solutions video now. I'll just do it right now. And tomorrow we'll just keep on going. Tomorrow we're gonna get into the polar form of complex numbers. It's going to be fun. We're going to actually figure out a way to do like the 7th root of I. And if you never wanted to know, it's too damn bad. I'm going to show you. Okay. That's enough, guys. Let me know if you need to hang out. Otherwise, you are free to go.
Neat stuff. See you later.
Thanks, Professor.
Sure.
Hey, Professor, I have another homework question.
Yes.
Okay, so section 10.3, number 18.
Okay.
Like, I guess sort of like we could do something like similar to this. Like,
Well,
I'm not sure if I wasn't doing, I was right.
Just tell me, what is y in polar?
R sine theta.
What's x?
R cosine theta.
Goes in. And then the one thing you can do you see what I'm saying? It's that simple. It's that simple. Now, if I see, now the one thing you could do after you do that is like kill an R. Are you with me? Both sides will have an R.
Yes, okay.
I know R squared, so you can kill an R. If I see this, I'm not going to do that because what is x squared plus y squared?
It's doesn't it equal R? R
squared, yeah. Good old Pythagorean theorem. So I'm not going to put R cosine theta in for x and R sin theta because I know what x squared plus y squared is. So I'm gonna if I'm you, I'm gonna have my four little conversions.
Mm-hmm.
sitting next to me as I do this homework.
Okay.
What to look for. 23 is a little bit more evil, but it's not that bad. You still have to, you just go back. Oh, you don't have to do 23, do you? Did I
No.
sign minus one? No. But here you would just put in r cosine theta, r sine theta, because it's minus. You can't, and then here you put a r. Does that make sense? I mean, so if you
Okay.
look for, you put r cosine theta, r sine theta, if there's no other more simple overarching thing, like the x squared plus y squared. Yeah.
So then eventually the r's you said just cancel out.
Yeah,
Yeah.
for number 18, you can cancel one r out, and that leaves one r over here, of course, right? Because the one that's going over here is going to be squared.
Oh, okay. Awesome. Okay, because because what I have left over is like r sine theta equals 4 cosine theta squared, and then
Oh, no. So you should get r sine theta equals 4 r squared cosine squared theta, right? Because you're squaring x, and
okay.
x is r cosine theta. So should be 4 r squared cosine squared theta. So if you cancel an r,
Okay. Uh-huh.
you have sine theta equals 4 r cosine squared theta.
Okay, I see that. All right.
The side that had more r should have an r left. Yeah.
Ah, okay. Got it. All right. Thank you.
You're welcome. Everybody else okay? If you're out there, I'll take that as a yes, and I will leave now. Pretend like you're here the whole time. Bye.